Okay, I'm going to use AutoCAD. Hopefully it doesn't 86 on me to do an example. Do this in 2D of how to go about doing a graphical solution of a circular dam gate problem. Remember that if in fact pressure acts perpendicular to a surface at any one point and that surface is curved, that means that the incremental tiny little force that's happening at that place is pointing towards the center of the circle. Therefore, that pressure on some does not have a resistive turning moment to spin about the center of that circle. That's why dam gates are made to be round, because you don't have to work against the pressure of the water to turn them. You just have to work against the weight of the gate. So let me go ahead right here and put up a big dam gate. There are many, many cool dam gates structures nowadays going into Venice. That would be in Italy. Potentially to New Orleans someday, and definitely into the Deltawerks in the Netherlands. Again, this is civil engineering. It's a pretty wide profession worldwide. So I'm going to go ahead and just draft a line here. I'm going to start with 0, 0, 0. I'm sorry, 0, 0. And I'm going to kind of draft off here around 100 feet. And I'm going to make that offset here. I'm going to make a 20-foot water surface. I'm going to get used to, now I'm going to do a couple things on my object layer here. I'm clicking on the layer. I'm going to give it, remember that thickness so you all can see, even though lines do not have a thickness. I'm going to give the water, I'm going to put the water on in living color layer because I've got that to be blue. I can start to use quick properties right there, so I can change the layer to in living color here. That's the free water surface. And I'm just going to put, hit cancel here, escape. I'm just going to put in a round gate more or less here. I'll do that offset 10. And I'm going to put an arc. I'm sorry, I'll go ahead and draw a circle from the end point there. Right, something like that. I'm just kind of just doing it so you can see, in fact, that I'm going to trim out line here from the end here, line from the end here, up here, trim out the gate. And I'm going to also, if you think about, let's see how this is going to work here, trim this out. Just going to ask the question then, what is the hydrostatic force on this gate? All right, so here's how you go about doing it. You realized you drafted it 1 to 1. This is 10 foot down here, so we only have a depth. I'm going to draw a line from near here, perpendicular to, so we have that height, if you would, 10 foot tall, right? So from here to here is 10 foot. And now what you've got to do is think about using some really cool sense of what does the pressure distribution look like? What is the hydrostatic force on that gate? First you have to realize, because all the little pressures are perpendicular to that, they're going to go directly through that center line there. Say offset through. Take that point through the end point of that. And now you more or less have two surfaces here, or two shapes you need to worry about. One is going to be the weight of the water acting down through the centroid of that shape, and the other one is going to be a triangular distribution down 10 feet. Pressure is 0 here. It goes to 624. And now you start thinking about setting up different scales. You want to say, okay, the scale going up is per square foot. Scale going over, maybe 1 equals 10. So I'm going to go a line here. I'm going to offset this, not 10 times 62.4, which would be 624. I'm going to go 62, maybe 6.2. Offset 6.24, 1 to 100 if you would. Offset 6.24. right? And then the hydrostatic pressure looks like from the end point there to the end point there. That is, right in here is going to be an area. We're going to have to multiply it by 100 to get pounds, and the centroid goes through the centroid. Same thing there. So let's go ahead and make a new layer and call it calcs. CALCS. We'll give that a new color. We'll give it the purple color, the white. Nope, we'll give it the magenta color. And then we start to use that tried and true boundary command, or bpoly. Bpoly. I'm going to go ahead and make it immediately a region. Click in here. That is one region. I'm going to make sure and change that last thing to the right layer, which we wanted it to be on calcs layer. So there you have one region, and we have another region. We should know this one already. We should know that the centroid is from the third from the lower end of offset of 3.33, offset of 3.33. That's a third from the heavy end. Hard to believe. Distance from near to perpendicular. That is 10, so that's 3.33. We know that it acts. Grab this here and trim that out. All right, so we got it some force, and we'll know the force of that is equal to the area under that. We can do that sooner or later with a field correct. So I'm going to go ahead and just move this off to the side. We don't need to use graphics except for this thing here. And we know this is going to have an area. It's a foot out of the board, so that has a volume. The volume times the density gets the weight. The weight acts through the center of mass, which is down. And so what we can do is, and say here, we can say mass prop. Grab our objects there. And our center of the centroid is 10.42 and 17.62, and its area is 16. Now, if you remember, this actually is 16 square foot. That would then be 16 cubic foot times 16 cubic foot times 62.4. And so, boy, you got to get out your pencil, write some stuff down. And so you're saying, well, is that right? It's 16 square foot. All right, 16 square foot times depth out of the board is 1 square foot. So that's 1 foot, 16 cubic foot times 62.4. And you know that there is a vector going down. Let's go ahead and remember, if we can, 10.4 and 17.6. So I'm going to now draw a vector line from 10.4, comma 17.6. That looks like it's about right going down. This vector, we know it was 10 gamma times 10 square foot times 62.4. That's 50 times 62.4. Starting to sound a little familiar, 3120. I'm going to keep here, circle from the end point there, and I'm just going to take a circle of 31.2. Boy, that's a little bit too far. Undo, undo, circle, end point 3.12 for 31.2 pounds, 3120 pounds, trim. Erase out. This one was 16 times 62.4. Sure, let's try it. Where's my calculator? 16, clear, 16 times 62.4, about what? 1 down. So circle, 1 down, and each one of these is 1,000. So I'm going to know that I'm going to go from here. I know this is this way, and I'm going to go lengthen, total, 1, that. Now I can add these together, move, add those vectors together from the end point there to the end point there. We have a resultant, you have the solution, you know that this vector is going to go through that line. I'll just end it there and hope you can have followed some of that stuff.